A manufacturer gets 10% of a certain part from plant A, 28% from plant B, and the rest from plant C. Of all the parts that come from plant A, 2% are defective. Of all the parts that come from plant B, 18% are defective. And of all the parts that come from plant C, 19% are defective. We need to find the probability that the part comes from plant B given that it is defective. So we're looking for the probability that it comes from plant B given that it is defective. I'll let defective be D. So that's what we're looking for. This is what's not known. And let's see what's given. They say a manufacturer gets 10% from plant A, so that means the probability of the part coming from plant A is 10%. 28% come from plant B, so that means the probability of coming from plant B is 28%, and the rest come from plant C. So all their parts come from either A, B, or C. The rest would be, let me see, that's 38. So the rest would be 62%. So plant A and B account for 38%, so the rest is 62%. All right, so now we have the probabilities. Those are the marginal probabilities of A, B, and C. Let's see what else they give us. They also say, of all the parts that come from plant A. So we're being conditioned on coming from plant A. We know already that the part comes from plant A, and it says 2% of them are defective. So the probability of being defective, given that the part came from plant A, is 0.022%. Of all the parts that come from plant B, 18% are defective. So the probability of being defective, given that we already know it came from plant B, is equal to 0.18. And lastly, the probability of coming from plant C, probability of being defective, given that we know it came from plant C, is 19%. So those are the given pieces of information. This is what they're asking me to find. I notice here that the probability they're asking me to find is an inverted probability of actually this one, right? So they're asking for B given that it's defective, and I know the probability of being defective given it came from B. So it's an inverted probability. So we're going to use Bayes' theorem. First, let's start off and look at what they're asking us for. They want the probability of B given D, which by definition is the probability of B and D divided by the probability of D. And let's see here. Do they give us any of those? They didn't give us the probability of B and D, nor did they give us the probability of D. So we need to find those things in terms of what's given. Well, I know one right off the bat. Right off the bat, I know that the multiplication rule for and, if I want to find the probability of B and D, then it's going to be the probability of B times the probability of D given B. What's good about both of those is I don't know the probability of B and D, but I know the probability of B, and I know the probability of D given B, and I can use those to find the one I want. All right, when I look in the denominator there, the probability of D, I don't have the probability of D, but I know a few things. One thing I know is that the total probability of D would be the probability of D and B plus the probability of D and A plus the probability of D and C, because those are all the possible choices. Like, that's exhaustive and mutually exclusive. You can't come from A and B. A part can't come from both. A part can't come from A and C. So they're mutually exclusive, but they're also exhaustive because all the parts either come from A, B, or C. All right, so if I find the probability of being defective coming from all three, I find the probability of being defective overall. So that's the total probability of being defective. And then, because I know the AND rule, I use it on top, right? I use the AND rule here to get this. I can use it on the bottom again. I already actually found the probability of B and D, which is the same thing as the probability of D and B. We already said that that was equal to the probability of B times the probability of D given B. So on the bottom here, we have in the first term the probability of B times the probability of D given B. But then I have to find those other ones, and I'm going to use the same formula. It's just the product rule for probability. So the multiplication rule says if I want the probability of D and B, I do the probability of D and A, I should say. I'm going to do the probability of A, which I know, times the probability of D given A, which I also know. And the last one I need to add in to get the probability of C, or D and C. So for the probability of D and C, I'm going to do the probability of C times the probability of D given C. So this is Bayes' theorem right here as it applies to the problem we are doing. So Bayes' theorem is going to allow me to just plug all these in. Let's see what we have here. So the probability of B was 0.28, and the probability of D given B was 0.18. Those were given. So the probability of B and the probability of D given B, those were both given. In the denominator, that term also occurs, 0.28 times 0.18. It's also down there. And then plus the probability of A. Well, the probability of A was given as 0.1, and the probability of D given A was 0.02. So that's going to be 0.1 times 0.02. 0.1 times 0.02. And then the last one is the probability of C, which was 0.62 times the probability of D given C, which is 0.19. So that's 0.62 times 0.19. And then we just do these calculations. All right, so the top there is 0.0504. 0.0504. The bottom, there's a 0.0504 as the first term, but then the next term is 0.1178, and the last term is 0.0020. Adding those all up, we get the denominator to be 0.1702, and then my final answer for the probability of B given D, is equal to 0.3173. And that's how we use the Bayes' theorem formula.